We had discussed the elementary particles and then the basic fundamental interactions that they undergo in the last discussion. In this, we will further discuss the elementary particles, some of their properties, and also understand what is the meaning of antiparticle in some sense at some basic level, and further go on to the Quark model, which explains or gives some understanding of the different compound particles like protons, mesons, pi mesons, etc., that had been discovered in both in cosmic rays as well as in particle physics experiments. So, to recap what we had discussed about the elementary particles and the forces in the last lecture, we said we could broadly classify the particles, elementary particles, into two categories. One is called leptons, the other is called quarks. Leptons are the ones which take part in weak interactions as well as electromagnetic interactions if they are charged, and quarks are, in addition to the weak interactions and electromagnetic interactions, quarks take part in the strong interactions as well, whereas the leptons do not take part in the weak interaction, strong interactions. Further, we said the forces, these or the forces the elementary particles experience, or the dynamics of these interactions are dictated by what are called the force carriers. We can think about elementary particles associated with these interactions. They are called force carriers, or we will see later on that they are actually also called the gauge bosons of the particular interaction corresponding to the particular interaction. So, for example, electromagnetic interaction is carried through the exchange of photons, and so photons are called the force carriers or the gauge bosons corresponding to the electromagnetic interactions. Similarly, for weak nuclear interaction, there are three such gauge bosons. One is a neutral gauge boson, and another one is, and the other two are charged gauge bosons, W plus minus. All of them, all the three of them having mass around 100 GeV over c square. And strong nuclear interactions are carried over through the exchange of what is called gluons. There are 8 different types of gluons, and they are massless. And then we also further discuss the need of an additional particle, an extra elementary particle called the Higgs boson within the standard model of particle physics. Of course, I should mention as an aside that there are other mechanisms which are proposed. There are different mechanisms actually which are proposed through which masses of the particles can be generated without, or either without any scalar field or with some composite scalar field. But these models are not tested yet, and the standard model also, the Higgs mechanism of the standard model is also not tested completely, in the sense that we have not proved or discovered the elementary scalar particle which is the Higgs boson. We did discuss a scalar resonance in 2012 with the mass around 125 GeV per c square, and which is a very good candidate for the standard model Higgs boson. Moving on, we will look at what's the meaning of these antiparticles today. Let us look at the beta decay. beta decay at the level of nucleons is basically a neutron changing into a proton with the emission of an electron and a neutral particle, which is actually an antineutrino. So, although I said this antineutrino, we will come to know what is the meaning of this antiparticle and what is the difference between neutrino and antineutrino, etc. as we go. So, if I consider neutron going to proton, the beta minus decay or a negatively charged particle, which is identified as the electron, very exactly the same, exactly similar to the atomic electrons, are emitted. And we discuss how this process would actually go through the weak interaction. The d quark in a neutron has one u quark, two d quarks. One of the d quarks convert itself into a u quark and a W minus. Remember, W minus is much more massive compared to the d quark if you look at the mass that we have listed in that. But one thing that can happen is that these W bosons need not to have the mass of the W boson, original real W boson. But you can actually think about a short duration in which this particle live, and therefore energy can be violated. And you can think about a particle, although it is actually in a real situation, real particle should have a mass of about 80 GeV. We do not have that much of energy in the d quark, but it can actually convert itself into a virtual W minus, which need not to have the mass or of the real particle. Okay, its energy can be smaller than that. This energy will be, or this W particle decays immediately to an electron and an antineutrino. So, this is the electron that comes out of this thing. So, if you look at the charges, d quark has minus 1 by 3 charge, which decays into a u quark which has a 2 by 3 charge plus, and W minus has minus 1 unit of charge. We are talking about charge in units of electronic charge. So, the total charge in the final state W minus plus u quark together is minus 1 by 3, which agrees with the charge of the initial particle, which was only the d quark. That is fine. And then when W minus decays, one of the final products is electron having a charge of minus 1 and the other one is neutral. So, charge is again preserved, no problem. Alright, so these are some of the things that we said earlier. So, quarks have all the three interactions, quarks are never found in free state. This is another thing. So, now we do not see the quarks in free state, but quarks are always combined to form a composite particle in that. And this electron has a negative charge. Think about a similar particle, but with electronic charge positive. A particle which is very similar to the electron, but with electric charge opposite to the electron, mass the same as that of the electron, is found. That is called the positron. These positrons are called the antiparticles of the electrons. So, we saw that in beta decay electrons are emitted. Similar to this, there is what is called the beta plus decay, in which you start with a proton and a proton is converted into a neutron and a W plus. Look at the charge again. Proton has positive charge 1 unit initially and neutron is neutral, W plus has 1 unit of positive charge. So, that is conserved. Or if you look at the quark level, a u quark from a proton is converted into a d quark. So, that initially you have u quark, 2 u quarks and 1 d quark, and finally, you have 1 u quark and d quarks. So, the U quark initially has a charge of plus 2 by 3. This is converted into a quark D quark of charge minus 1 by 3 and W plus of 1 unit of positive charge. So, total in the initial and the final states, the charge electric charges are plus 2 by 3, and this W plus decays to a particle which has the mass same as that of the electron and a neutral particle which is similar to the neutrino, and the charge on the electric charge on the electron like particle is now opposite to that of the electron, which is positive 1 unit. This is basically the positron, which is the antiparticle of electron. As although we said this, if you look at the energetics, mass of the proton is only 938 MeV per c square and mass of the neutron is 940 MeV per c square approximately. Free protons therefore cannot undergo beta plus decay, because initial energy available, if you go to the rest frame of the proton, is only 938, which is less than the mass minimum energy required for the particle to the neutron to be produced. So, this proton decay happens only within the nucleus. Beta plus decay is observed in nature. There are nuclei, isotopes, which are unstable, decaying through the beta plus emission or positron emission. You can think about positron emission tomography in fact, and ask yourself what exactly happens in that case. In fact, the protons do not decay at all. It is not that protons do not decay through beta plus emission, but protons are very stable, and the whole construction of the universe, whole construction of everything that is there in the owes somewhat to this stability of the proton. Again, think about what happens if proton would have been would not have been stable as it is and could have decayed fast. Now that we said what is an antiparticle, we will not go into the details of this. There are proper ways to understand the antiparticles. What we can do is to compare or to understand it through the wave functions in quantum mechanically, the wave functions of the antiparticles, and then ask questions how one goes from, or one actually differentiates this particle and antiparticle wave functions, etc. So, but here we will not go into that, rather we will just list the particles that we know of, elementary particles and their antiparticles. For example, electron antiparticle is called positron, which is symbolized as E plus instead of E minus for the electron. Similarly, muon, mu minus is an anti-muon as the antiparticle, which is denoted by mu plus, and tau minus has an antiparticle, anti-tau lepton, tau plus. Neutrinos, electronic neutrino has an electronic antineutrino, muon and neutrino has a muon antineutrino, and tau neutrino has a tau antineutrino. Up quark, anti-up quark. So, up antiquark, charm quark, charm antiquark, top antiquark, down quark, down antiquark, strange quark, strange antiquark, bottom quark, bottom antiquark. And usually the notation is that for quarks you put the letters U, C, T, B, D, B, D, S, B, and for the antiquark quarks you put a bar on top of the letters denoting this corresponding flavor type of the particle quark. Photon and Z particles are their own antiparticles. Okay. All these are consistent interpretations and consistent picture that quantum mechanically you can work out and then you could live with. But then W minus and W plus can be thought of as antiparticles of each other. Gluons of antiparticle called anti-gluons. There are differences there. Of the particle and antiparticle, we can say their as we mentioned, like in the case of positron and electron, mass remains the same, spin remains the same, electric charge is reversed. There are other quantum numbers also which are reversed, additive quantum numbers, any of those are reversed. We will come to a little later why in beta decay an antineutrino is produced, not a neutrino is produced. If you remember the discussion where we actually necessitated the presence of an antineutrino or a neutral particle, either so far as whatever we have discussed, or if you consider all the aspects of particles and their interactions that we considered so far, there is no need to actually have an antineutrino to be put in there, or it could have been a neutrino or an antineutrino. But for reasons that we will explain in a little while, it is an antineutrino that comes there. And experimentally we have actually shown that it is not the neutrino, but the antineutrino that is there. And there is a very definite way of experimentally distinguishing these two particles, although the charge of these two particles are the electric charge are the same. Mass is 0 almost, or mass is anyway the same for this thing. There should be some other quantum number which distinguishes between these two. We will come to what that quantum number is later. So, let us come back to what we mentioned in the second slide. Quarks are not free, but they are always found in bound states. Quarks and antiquarks form bound states called mesons. For example, we have pi plus positively charged pion, which is made of a u quark and an anti d quark or d antiquark. Pi minus, on the other hand, is made of a u type antiquark and a d type quark. So, if you look at the quark contents of pi plus and pi minus, you will see that basically instead of u quark, its antiparticle is there. Instead of antiquark d, you have a d quark there, or d bar is the antiparticle of d in that sense. So, now therefore, pi plus is an antiparticle of pi minus. So, one of them can be thought of as the particle. If you consider one as particle, the other is an antiparticle of it. These are actually mutually, there is nothing strange about antiparticles otherwise. So, therefore, no need to actually say which of this is the actual particle. Those kind of questions do not make sense. It is only that one is an antiparticle of the other. But there are other aspects when it comes to normal matter. We have seen only particles in the normal matter. We do not have particles, normal matter made of antiparticles at all. We will come to this aspect again later. Okay. So, similar to the pions, pi plus and pi minus, you also have a pi 0, we will mention that later. There is another meson called K plus, positively charged K meson or kaon, which is made of u quark and an S bar, anti-quark of type S. Similarly, there is a K minus which is made of u bar and an S. And again K plus and K minus are antiparticles of each other. D plus is another meson which is observed. It contains a C quark, a charm quark and a D bar. D minus opposite to this, and a C bar and a D. B plus U and a B bar. B 0 S is B S bar. Three quarks form bound states called baryons. For example, p quark, p denotes proton, which has a quark content of UUD. Then you have a neutron which has a quark content of UDD. Lambda has a quark content of UDS, another baryon. Then there are doubly charged baryons, delta plus plus content u, omega minus s, lambda b u d b. You notice that in none of these examples we have a top quark appearing. It is not because I just randomly chose the examples like this and that group did not have the top quark, but it is because the top quark cannot form bound states or does not have any bound states. There are no bound states of top quark found. All other quarks U, D, S, C, B, all these 5 quarks are found to form bound states of different masses, different properties, etc. The reason for top quark not forming bound states is the following. The mass of this is very large. So, it can be produced only in very high energy collisions, high energy experiments. And once these quarks are formed, since they cannot appear, they cannot be live as a free particle. Just to mention, this particular property is called confinement, that quarks are confined to bound states. This is something which is somewhat ill understood even today. Okay, so the quarks cannot form bound states. The quarks usually pick up other quarks from the vacuum, okay, or form bound states with other quarks available. Top quark is produced and then it could also look for other quarks to form pairs or to form bound states of quarks or quarks and antiquarks. But before it gets this time to look around and then pick up these particles, it decays. This is actually a very heuristic way of saying it. Okay. It does not really have enough time to form bound states. Technically, this is called hadronization, that formation of the bound states. So, top quark decay time is so small that it does not have enough time to hadronize. So, that is the reason why we do not find top bound states of top quark. Now, there are a lot of hadrons that we have discovered over the years in high energy collision experiments as well as in cosmic rays. What are cosmic rays? Cosmic rays are particles which are actually coming from outside the Earth's atmosphere, could be partly from the solar system, the sun itself, from the nuclear reactions of sun. There are particles which are coming out, and similarly from other stars or from other interstellar objects or galactic objects or any other objects, astrophysical objects or any other source that is outside the Earth. Different types of these cosmic rays come in, and then as we mentioned some time earlier, some of these particles, pions, etc., are found in these cosmic rays, positrons, electrons, many antiparticles and particles. And in high energy physics scattering experiments, we could produce many of these particles again, which are otherwise not naturally occurring in normal matter, like pions. We do not have atoms with pions inside that in some form, but we have atoms with protons. We do not have atoms with lambda inside that. We have not seen kaons in nature, in normal matter. But these can be produced, and then we have seen them, discovered them in experiments, scattering experiments, and we also seen them in cosmic rays. So, the first step when you have many such things, such particles and such resonances, is to understand them by classifying them. Okay. Actually, now we will go one step before and start looking at the particles as historically they are seen. before they were identified as quark bound states, what was the status? We knew we had a lot of protons, I mean we have protons and neutrons in normal matter. We knew there are particles called pions, kaons, etc., but we did not know exactly what they are, whether they are elementary or whether they have some composites, etc. This information came at a later stage, experimental, in 60s. But before that, we had all these particles, there are not many of them, and then we had to understand them. So, classifying them was one task to start with. One way people thought about it is by using some kind of a symmetry principle. So, this symmetry principles and the way to understand particle properties through symmetries have been are used extensively in particle physics. We will see that. One particular this thing very useful in classifying the particles, okay, at this stage, is assigning them a quantum number called isospin. This is very similar to the ordinary spin, in the sense that when we do the algebra, when we actually treat them mathematically, or when we look at the symmetry groups or the mathematical form of the symmetry, it is exactly similar to the spin. So, what people found is that successfully, consistently, one can assign isospin to these hadrons which are observed. So, any of the bound states of the particle quarks we will call hadrons. Mesons and baryons together are called hadrons. Mesons are hadrons with a quark and an antiquark. Baryons are hadrons with 3 quarks in it. Coming to the isospin, as an example, you consider the group of 3 particles. You have seen pi plus, pi minus and pi 0, and it is found that they all have similar mass around 140 MeV per c square, and therefore, people group them under one single isospin group with isospin equal to 1 and I 3 equal to plus 1, 0 and minus 1 for this. Similarly, the kaons k plus and k 0, see when I put these symbols, then it look natural to call them in a group, but you think about an experiment where you actually discover some particle, positively charged particle, some particle which are negatively charged particles, some particles which are neutral. So, to classify them, you have to look at other properties, like you have to collect them in with those having similar mass, etc. For example, k plus is not grouped together with pi minus because they have different masses. Kaon so have masses around 500 MeV, whereas pi minus have mass around 140 GeV. So, it was therefore other consideration, not just the charge that will dictate these things. So, there were only 2 particles of this kind with 500 MeV per c square mass and positively charged and 0 charge. That is not exactly true. There was also a k minus which was found later on, but okay, and also another neutral k 0 bar, which is antiparticle of k 0. So, there had been many different types of iterations, etc., that has gone through and models were proposed, and then this is what something like the end result that we are discussing. So, there is a k plus and k 0 which can be grouped under I equal to half, I 3 equal to plus and minus halves, and all other mesons could also be classified under this isospin grouping. Now, similar to this, baryons could also be classified under this or grouped through as isospin groups. For example, a proton and a neutron together can be thought of belonging to an isospin group of isospin half and sigma plus sigma 0 sigma minus another baryon group of baryons again with similar mass can be grouped to a group of isospin 1, and lambda there was nothing to club that with the same mass. So, this is a particle with isospin equal to 0 standing on its own in a single group, in a group of single particle. So, other mesons and baryons could also be classified exactly in an exactly similar way, and now you collect them in this fashion, and we did not know about the structure of this or quarks. But then if we imagine this particle as made of substructures called quarks, or you can actually give some explanation for this kind of grouping. Why there are 3 pions with in the isospin equal to 1 group, why there are 2 kaons in isospin equal to half group, etc., or why the protons and neutrons are together in isospin half, etc. For that you need to look at the quark content of these things. So, now we know that already we mentioned that there are U quarks, D quarks, etc. All these quarks were actually discussed. So, let us revisit that again, along with the other properties. We now have to assign what is the isospin of this quark. So, if you look at the U quark and D quark, put them in an isospin 1 group, and I 3 equal to plus half for U quark and minus half for D quark. Put S separately with isospin equal to 0. Okay. Now, in a similar vein, you can look at the anti-quarks, a D bar and a U bar minus, okay, and an S bar in I equal to half U bar and D bar, and I 3 equal to plus half minus half. S bar is again isospin 0 group. You see that I have put a minus sign there. What is the meaning of putting a minus sign in a symbol? So, basically, when I put these symbols U, D, S, U bar, D bar, S bar, we can also think about the wave function or the associated wave function representing these letters or the symbols representing the wave functions of this corresponding particle. If that is so, then we need to put a minus sign, relative minus sign in the D bar U bar case, and the D bar quark will now have I 3 equal to plus half, and U bar quark will have I 3 equal to minus half. On the other hand, in the case of quarks, U had quark I 3 equal to half and D had I 3 equal to minus half. This can be done if you understand how to go from one to the other. Okay? Or the other way of saying it is that for consistent quantum mechanical picture, wave functions of U and D quark, okay, if you consider and transform that to anti-quark wave functions, then it will go from U to minus U bar and D to D bar. And if you look at the isospin of this particle, the transformation will tell you that U goes to a U bar, and the isospin third component will go from corresponding to this will be half in the case of U and then minus half in the case of U bar. One could also imagine the minus sign along with a D bar quark and U bar quark with a plus sign relative to the U and D, but then therefore, it is only the relative sign between these D bar and U bar which is important. Some explanation and some elaboration on this is done in Introduction to High Energy Physics by Donald H. Perkins. You could also consult other books discussing quark model to understand the technical details of how this minus sign comes, etc. We will not discuss any further this aspect in our discussions. Now, but when we actually combine two quarks or a quark and an anti-quark, the isospin of that combined state will follow an algebra or an algebraic relation very similar to or exactly similar to in fact that of the angular momentum addition, which is what we are familiar with, I believe, from your quantum mechanics courses. Now, consider the U quark and D quark, as we said just now, I is equal to half and I 3 equal to plus half for U quark and minus half for D quark. And for the anti-quarks, we said we have a D bar and a minus U bar with I 3 plus half. Let us form a combination of this U quark and this U D system, quark system, and U bar, D bar anti-quark system. What are the things that we can form? This is similar to combining a spin half system. So, let me denote the IQ, denote the isospin of the quark system as IQ, which is half. We take that, combine that with IQ bar, which is again half. Angular momentum addition tells us that the resulting combined system can have an isospin either 1 or 0, half minus half or half plus half. This is based on the angular momentum addition rules. Consider the case of I equal to 1. Again, if we think about I equal to 1, I 3 equal to 1, there is only one combination that can give this in terms of the quarks, which is I q equal to half, of course, that is the only thing, I 3 q equal to plus half and I q equal to half, q bar equal to half and I 3 q bar equal to plus half. So, that I 3 q and I 3 q bar adds up to 1, which is the I 3 q of the I 3 of the combined system. And ask the question, do we have a particle like this found in nature? The right hand side will tell you that it is basically U quark, which is I q half and I 3 q equal to half, and a D bar quark. So, this is basically the system on the right hand side. Do we have a physical particle or a meson corresponding to this? Charge is equal to plus 1 because U has charge of 2 by 3 plus 2 by 3 and D bar has charge of plus 1 by 3. This can be thought of as our pion. You want to see what are the other possibilities when you combine an IQ equal to half and IQ bar equal to half. For that, you consider this I equal to 1, I 3 equal to 1. Usual way to do it is to actually operate the step down operator on this, operate on this I equal to 1, I 3 equal to 1 by a step down operator, and we will get something into I equal to 1, I 3 is reduced by 1 unit and equal to 0. What is this something? Something is, so in a general case, for a step down operation is I minus I 3 equal to I plus I 3 I minus I 3 plus 1 under root, that is the coefficient that will come with this, and I equal to 1, I 3 equal to 0. Oh, sorry, I 3 equal to, so I should write the general form from here. So, it is I I3 equal to I3 minus 1. Then we can actually apply this here in the case of I equal to 1, I3 equal to 1, and then we will see that I minus I equal to 1, I3 equal to 1 is equal to 1 plus 1 is equal to 2 into 1 minus 1. So, that is root 2 into I equal to 1, I3 equal to 0. Similarly, you can apply this I minus on IQ equal to 1 by 2 on the right hand side of that equation. Earlier we had I3q equal to half, IQ bar equal to half, I3q bar is equal to plus half. This is equal to, as per the formula equation that we had, this is equal to half plus half, that is equal to 1 into half minus half plus 1. So, that 1 into 1. So, it is actually 1, that is the coefficient. So, first we will apply this I minus on the Q system, and then that will give you IQ equal to 1 over 2 and I3q equal to minus half, the other one remaining the same, bar 1 over 2, I3q bar equal to half. But then plus IQ equal to half, I3q equal to plus half, IQ bar equal to half, I3q bar is equal to minus half. And this, if you look at, is nothing but I3q corresponds to a D and I3q bar corresponds to a D bar plus actually I3q plus, that is a U, but I3q bar minus half is a U bar with a minus sign. So, that is why I put a minus sign there. So, this is the quark content of I3 equal to I equal to 1, I3 equal to 0, which means, so we can ask if there is a particle like that, and indeed we can identify pi 0 with this, but you had a root 2 there in as a factor. So, it actually is root 2 pi 0 is equal to d d bar minus u bar, or pi 0 is 1 over root 2 d d bar minus u bar. We will look at one more example and then further discuss this quark contents of mesons, different other mesons, and also that of the baryons in the next discussion.